Okay, Morgan.
So I can introduce our first speaker is, do you like that? It's good to have two hosts. Some hosts are slightly less prepared than others.
No, it's okay. I think I can do it.
Oh, you're
now.
back. Okay,
yeah,
go.
I'm back. So it's a great pleasure to introduce Anna Ho, who is currently a Miller Fellow in Berkeley. And she was an undergrad at MIT where she worked on millisecond pulsars. Short one this time. Then she moved to Caltech as a grad student, but before then she took a year off as a Fulbright Fellow at MPIA, and there she did really important work extending the Canon code or measuring stellar abundances from the kind of domain it has been trained on SCSS apogee data into hundreds of thousands available on most spectra. So I feel like many people in our community expected Anna to go to Caltech and then use Keck and like just continue along this this line of research. However, she surprised us all by getting involved with the ZTF and starting to study transients and finding like really opening up this new landscape of so many different types of events that we now know of and we'll hear about in the next 20 minutes. So thanks, Anna, take it away.
Thank you for the very kind introduction. Can you all hear me and see my slides? Okay, great. So I'm going to tell you about some of my recent work studying extreme cosmic explosions. And I thought I would start by explaining what I mean by extreme. This is a cartoon showing the landscape of optical transients or cosmic explosions in the year 2005. The x-axis shows the timescale of the transient from 1 day to 100 days. And the y-axis shows the peak luminosity in V-band absolute mag on the left-hand side and ergs per second on the right-hand side. So at the time, there were basically 3 major established classes of transients. But a few years later, thanks to wide field untargeted optical surveys, we filled in many of the so-called gaps in luminosity space and began to push to faster timescales. So what I've been doing for my work is trying to push to even faster timescales and higher peak luminosities. For a long time, this was exclusively the realm of afterglows to long duration gamma ray bursts, which we would find in targeted follow-up observations to discoveries by high energy satellites like Fermi or Swift. But today we can find routinely optical transients without relying on a GRB trigger that live in this part of phase space. And that's because we live in an era where every night a whole suite of high cadence surveys are patrolling the sky looking for transients. So the one that I've been particularly heavily involved with is the Zwicky Transient Facility, or ZTF. So I thought I would give you a sort of window into the transient astronomer life with an example of why it's sort of challenging to do astronomy in the top left part of phase space here. So this is an example, this is an event that I discovered earlier this year. This is a transient that looked very much like an afterglow to a GRB, but it was not picked up by high energy satellites. So I'll walk you through the timeline in observer frame, estimated time since explosion in the observer frame on the bottom, and then in the rest frame on the top, because this is at a redshift of 2.9. So we discovered this event with ZTF at 19.5 mag. This was it, but it was quite red, and that's what kind of tipped me off. So I immediately triggered photometry, and we showed that this was fading quite quickly. We triggered a TOO on Keck, so I got a spectrum with LRIS, and that's how we measured the redshift of 2.9. I triggered Swift and measured X-rays. I got another epoch of photometry with Gemini, which showed that this was a broken power law light curve, and finally triggered the VLA and also got a radio detection. So this was all the data that we got for this object. It was all obtained in the first 10 days observer frame since the explosion, and that's why this kind of work is challenging. But it's worthwhile because it teaches you about the extremes of how massive stars can end their lives. So we have this traditional story where massive stars end their lives by developing an iron core. They collapse and explode in a core collapse supernova and leave behind a neutron star or a black hole. But today, and I think especially in the last few years, we think we've come to appreciate that the real story is far more complicated than that. And there are 2 complications that I'm particularly interested in. One of those is that some stars seem to launch relativistic jets when they collapse, via some kind of compact object phenomenon. And then the other is that some stars seem to undergo very intense mass loss of some kind, just in the final days to weeks of their lives, which I like to call death omens. And then when the star explodes, it collides with this dense material and produces a fast and luminous optical transient from circumstellar interaction. So the question is why, these phenomena are probably quite rare, but then the question is, why do some stars do this while others don't? And in trying to answer that, what I think is interesting is we get to revisit some of the basics of stellar evolution, so the importance of factors like rotation, metallicity, multiplicity, and mass loss, as well as the basics of how stars explode in the first place, and then the physics of how jets are launched and propagate through matter. So that's what I think is sort of astrophysically interesting about this top left part of optical transient phase space. So when I first started working in this field, I was particularly focused on this phenomenon of relativistic jets. The canonical example of this is long duration gamma ray bursts, which we believe are associated with core collapse supernovae. And of all the GRBs close enough where we could actually spectroscopically classify the supernova, it's always of the same type. So the spectrum is a 1CBL. So that means 1C means that there's no hydrogen or helium, and then BL stands for broad lines, which means that there are very broad absorption features, which presumably come from high velocities in the ejecta. So I thought I'd show an animation just to bring everyone onto the same page. So this shows a GRB progenitor. The core is collapsed into some compact object and launched a jet. The jet tunnels through the star, breaks it at the surface, and then escapes into interstellar space. It collides with ambient gas and dust, and this produces synchrotron radiation all across the electromagnetic spectrum, which we call the afterglow, and which we can observe with our optical telescopes and radio telescopes on the ground, and we believe out to large viewing angles away from the jet. But in order to see the prompt burst of gamma ray emission with a satellite like Fermi or Swift, we think that you have to be looking directly down the barrel of the jet. So that's the basic model of GRBs. But what I think is a little bit troubling is that the circumstances required to produce a GRB are quite contrived. So the jet has to get out of the star, which is collapsing in. The jet has to accelerate materials to ultra-relativistic speeds. So it actually seems more natural to think that GRBs are just the extreme of a whole continuum of phenomena that extend all the way down to even ordinary supernovae. So there's, perhaps there are dirty fireballs. These would be low Lorentz factor jets that might produce an afterglow but no GRB. There might be choked jets, so jets choked either inside the star itself or in some kind of surrounding CSM. So I set out to look for some of these things. And the problem is you can't rely on a GRB satellite because they won't necessarily produce GRBs. So my approach was to search for fast and luminous optical transients. So that's what brought me to this line of work. Along the way, I also became very interested in this phenomenon of stars exploding in dense CSM, which presumably got there via some late stage mass loss. We have now with ZTF been able to find these untriggered afterglows to gamma ray bursts, which is very exciting. And then also I've become interested in this other phenomenon called low luminosity gamma ray bursts and trying to find them using optical surveys as well. So I don't, obviously I can't talk about all of this today. And so what I thought I would do is just focus on this detour actually that I took, which is also related to relativistic explosions. And then I'm happy to talk about any of these things later on Slack or one-on-one if you're interested. Okay, so the beginning of my detour was on the 16th of June, 2018, when the ATLAS survey, which is another wide field optical transient survey, reported this transient that just coincidentally got the name 2018 COW, very nearby at only 60 megaparsecs. And it was immediately interesting because it was one of the fastest rising, most luminous transients ever discovered. And I was particularly interested because there were early reports of broad lines and X-ray emission, which is kind of what you would expect from a relativistic explosion. So I immediately triggered radio observations, which is a basic expectation for these kinds of explosions. To put my observations into context, here's a collage of radio light curves of various stellar explosions, low frequency observations, so with facilities like the VLA on the right-hand side, and then high frequency observations, so millimeter wavelengths with facilities like the SMA and ALMA on the left-hand side. And you can immediately see the left-hand side is much emptier than the right-hand side. That's, historically, it's been much less common to follow up stellar explosions at millimeter wavelengths. But 18 Cow was very nearby and discovered early, so this seemed like a good opportunity to try. And sure enough, with the sub-millimeter array, we found really quite an unprecedented millimeter light curve. So it was sort of double peaked, it had this very steep drop. We actually resolved the rise. We actually detected it at nearly a terahertz with band 9 at ALMA in a TO sort of follow-up DDT observation. So this was really surprising. And then the next task was to try and interpret this strange emission that we observed. So now I'll talk about that. So there's this classic diagram from radio supernova astronomy, where you plot on the x-axis the time of your observation times the frequency, and on the y-axis you plot the peak radioluminosity. And so I'm throwing on here a bunch of different stellar explosions, and 18 Cau is just way up here from our ALMA observation. So observationally, the question is, what does it mean to be on the upper right-hand side of this diagram? You can draw lines of constant velocity, so the relativistic explosions are here. 18 Cau, the ejecta speed was 0.1 c, so actually nothing really spectacular, so that's not the answer. You can draw lines of constant CSM density, which correspond to a mass loss rate, and so clearly that's part of the story, and I think that's usually what people think of when they think of high frequency observations. But that's not the whole story, because you have to explain the y-axis. And so in our paper, we showed that the peak radioluminosity is directly proportional to the energy thermalized by the shock divided by the shock radius. So the way to say sort of what does luminous millimeter emission mean is that this is what you get when you have an energetic explosion in a dense medium. And then millimeter observations are actually essential if you want to study the innermost CSM, which corresponds to the most recent mass loss history of the progenitor. So that was our conclusion. And I think what's promising for millimeter observatories is that 18 Cau is probably not unique in having these properties. So now I'm showing the low frequency light curve as well. And at early times, so it was doing strange things at late times. At early times, though, it looked actually kind of similar to other supernovae that we've seen. And looking back at some of the data for these other events here, there are 2 hints here. I think it's actually quite likely that a number of these were also bright millimeter transients at early times. It's just that nobody conducted those observations. So I think, yeah, I think the future is bright for millimeter time domain astronomy. Okay, so that was the focus of my, what I wanted to focus on was my millimeter observations, but just to conclude, I want to go through some of the other properties of this transient. Many people have worked on this, so just to speculate as to what it might be. So we observed very luminous variable X-ray emission, which I and then other groups have attributed to some kind of newborn compact object. There was obviously the fast and luminous optical emission, which tells you something about the structure of the CSM. There was hydrogen and helium and emission in the optical spectra, which, so clearly this is some progenitor distinct from GRBs. There was this fast forward shock, which I just talked about. We know that this must be somehow anisotropic. This is showing jets, but that's probably not the only possibility. And then finally, the host galaxy was a dwarf galaxy, kind of like GRBs. So that suggests that these progenitors have something in common in terms of their pathways. But since then, I think the consensus has become that these types of transients are rare. I've looked very hard in ZTF, and others have looked with other surveys. The rate is probably, certainly less than 1% of the core collapse rate, maybe even closer to 0.1% of the rate. We have found 2 other of these events. So we found one in ZTF. So what I'm showing here is we're kind of filling things in the upper right-hand side of this phase space. I also drew the second point here. This is a late time radio observation. So if you only observed with radio telescopes when it's bright in the radio, you can see it would look actually quite normal. And so this is just an example of why it's important to observe at high frequencies at early times. Okay, so that's, I think, all I have time to say about 18 Cau. As I mentioned, I looked quite hard to find more of these in ZTF. And a few months actually after 18 Cau, I found what I thought was going to be another 18 Cau in the ZTF high cadence survey, but which actually turned out to not be that. It turned out to be a 1C broadline supernova. So this, just to remind you, is the special type of supernova associated with GRBs. So kind of by accident, I was brought back to what I was originally looking for. This is the beautiful light curve from the ZTF high cadence survey. And I'll just highlight a few of the most important features. So you resolve this amazing rise of over a magnitude per hour in the optical. It was very luminous and blue at peak, which is why I thought it might become another transient like 18 Cau. We actually were able to detect this event prior to the explosion by stacking images, which I think is the first time that's been done, at least for a 1C broadline supernova. And after around 8 days, the spectrum, that's when the spectra really started to look like ordinary 1C broadline supernovae. So in my talk, I'll focus on interpreting this very strained light curve, but I do want to mention that we have an enormous amount of data on this object, which is enabled by the fact that we discovered it basically right at the beginning when it was rising, including what I think is the earliest spectral sequence of any stripped envelope supernova. Okay, so how do we explain this light curve? So ordinary 1C broadline supernovae, these are a few from the literature. We attribute their light curves to the radioactive decay of nickel-56. That mechanism really doesn't work for this one. It was rising way too quickly and much too high a peak luminosity. And so what I want to suggest is that instead, the mechanism powering the peak was shock interaction with a dense shell of CSM that is confined. So it just drops off abruptly in density, kind of at the edge. So the structure of this, we have a star 10 to the 10 centimeters or so, put the shell at 10 to the 14 centimeters. The star explodes with some ejective velocity, collides with the CSM, and then you get this shock moving at V shock. Photons are able to escape when the optical density, or the optical depth drops to C over V shock. And so you get this, you can think of as a CSM breakout. Then the time scale of the transient depends on the kind of width of this layer. So it's the width of the layer divided by the shock velocity. And with this kind of setup, you can get a transient that peaks in the optical UV on the time scale of a day. And the peak luminosity of that transient is the energy deposited in this layer divided by the crossing time. And so you can see that I think it nicely explains the properties that we observed. So to test this in more detail, I worked with David Katami and Dan Kaysen at Berkeley to run a 1D simulation in Castro. So the parameters that David put in, are 1C broadline supernova energy, so 10 to the 52 ergs, and then a shock velocity of 0.1 C. This is the shell properties, and this is showing the simulation results compared to our data. So the top panel shows the evolution of the photospheric radius, and then the bottom panel shows the evolution of the effective temperature. It peaked at 50,000 Kelvin. This is just the CSM interaction, and this is just adding in some 1C broadlined data from the literature. So I think this picture nicely explains what we saw. I want to mention something that initially got me kind of confused. So 18GeP has one analog of the literature. This is a 1CBL at higher redshift. And they also attributed this to some kind of CSM interaction. But when I compared our shell properties, I realized they were quite different. So I was getting something 2 orders of magnitude higher and an order of magnitude smaller for the shell mass, despite the light curves being quite similar. And so the reason for this, as a word of warning, is that I'm assuming shock breakout. They assumed that the shock breakout was over and that the optical emission was dominated by the post-shock cooling emission. So you just have this hot expanding ball of gas, basically. And there are relations in the literature that people commonly use to do this kind of modeling, but you get quite different answers, and you can reconcile this if you make the same set of assumptions. But yeah, so just a warning if you're trying to use shell masses and radii from the literature, is you have to see what exactly people were assuming powered the optical emission. Okay, so in summary, this event, I think we have a couple of lines of evidence that this was some kind of 1C broadline with enhanced end-of-life mass loss. There was the direct detection of some kind of pre-explosion emission, and then indirectly we saw the interaction of the ejecta with this pre-shed emission. I think this is quite unexpected in strip stars as far as I know. There are some ideas for how this might come about, but I think this is something I'm interested in learning more about. I think it's particularly unexpected in these GRB types of supernovae. I think there have been some predictions that you might get mass loss from rapid rotation kind of along the equator. This also made me interested about whether a CSM like this, how this would actually affect the propagation of a jet. So this is something I've worked with Paul Duffel here about. I think there's some disagreement. It's been argued that a jet would be completely choked, but I think in our work, we've found that that's actually not the case. Finally, I think in the future, we'll be able to establish what fraction and type of stars exhibit this behavior in sort of 2 different ways. The fast-luminous transients are well suited to a shallow high cadence survey like ZTF. And I think the study of this pre-explosion emission is basically perfect for a facility like the Rubin Observatory. So that's something I'm excited about now. Okay, so I think that's all the time I have. I obviously didn't talk about everything that I've been thinking about in the last few years, so I thought I would just leave a list up here, and that way you know what you can ask me about on Slack or individually later. So thank you.
Thank you so much, Anna. Yay! We're doing our best to line up our future backup careers as radio show hosts. No, thank you very much for a really beautiful talk, and yeah, let's open for some questions. Starting from the Slack, Floor has a question about 2018 cow. There we go. You all get really good at reeling off these numbers. And so looking at the millimeter versus longer wavelength slide,
yeah.
Flora is asking, it looks like the 18 cow has a steeper decline.
Yeah.
And could you tell us more about this?
Yeah, I don't think we really, so when we first saw a steep decline actually in the millimeter, and we attributed this to a drop off in the density of the CSM. So the idea was that you had 10 to the minus 2 solar masses of material confined to 10 to the 16 centimeters or so. And so that explained the drop off. But then seeing this at low frequencies, I don't think we really know. I guess I can think of two explanations for why you would get something like this. Either you run out of stuff to interact with, so it reflects the structure of the CSM, or your energy input is actually dropping off. So maybe this engine, whatever it was, ended or shut off somehow. But I think we're not sure.
Okay. Floor, do you want to add to that at all? Follow up? I guess I have another related question, which comes from Paul Duffel, and that's, so I'll read his question, but could you get this from a jet CSM interaction, this being the second transient you were talking about? And kind of relatedly to what you were just saying, can we use the multi-wavelength observations to disentangle like geometry versus energetics? Sort of like, can you combine, for example, millimeter observations and the longer wavelength radio and even the optical and say something about like whether it's a shell, for example, or a continuous distribution, or if it's a conical outflow versus a spherically symmetric? Like, what are the limits of what we can do?
Yeah. So I guess the first question, I think, was whether there could have been a jet. So we have no evidence for a jet. So the radio, there's non-detection in the radio, non-detection in the millimeter, non-detection in the X-ray. And I followed this up with radio out to quite late times in case there was some late rising but successful jet. So at this point, that seems unlikely. I don't think I'm reluctant to kind of invoke a jet unless one is actually needed. And so I think what we saw can be explained by this CSM interaction model. And so I'm reluctant to invoke some hidden choked jet of some kind. I guess the energy would be the thing that sort of is hard to explain, but that's the case for all the 1C broadline supernovae. They're all 10 to the 52 ergs, and that's difficult to explain with just a simple neutrino powered explosion. But observationally, I think we don't have evidence for a jet. Then I think the other question was how you can disentangle, how to talk about the geometry. So this, when people think of CSM interaction, I think they usually think of emission lines in optical spectra, radio emission, X-ray emission, but we didn't have any of that. So the spectra showed no emission lines at any point. We had spectra throughout the evolution of this transient. But I think that is naturally explained if it's just a shell where it's very confined and there's no kind of extended material going out to larger radii, because then by the time you get to peak light, the idea is the shock has swept up the shell. So there's nothing more to sort of interact with and produce emission lines. And then after this, you're just sort of done. So I think from the lack of emission lines, we can actually say that the shell seems, that supports this shell confined idea, whether it's toroidal or sort of an actual shell. I think we have no way to disentangle that at this point.
Interesting. So Josh Grinley asks whether this could be an off-axis GRB, in which case one is seeing a structured jet that might appear as a soft X-ray outburst. And maybe that relates to what you actually were just raising about constraints.
Yeah, I guess we
viewing
saw
it?
no, yeah, from my work with Paul, it seems like this kind of CSM, if there was a jet, the jet would have just gone sailing through
Interesting.
it. Maybe it would have been decelerated, but it would not have been stopped.
Hmm.
So I did look for an off-axis jet and found none with our radio observations, even at quite late times. So it seems at least not a jet like a classical GRB jet.
Interesting. And can I interrupt there with my own question? Is it the case that the CSM density is high enough that it would be radioluminous kind of thing?
Oh, right. That's a good question. I guess, so, right. When I say that I didn't detect a jet, what I really mean is I put some constraints on sort of what could the density have been and what could the jet energy have been. And I don't, off the top of my head, I don't remember what the CSM density is constrained to being. But I think for sort of normal GRB properties, we didn't see what one would expect.
I see. Interesting. And Avi Loeb asks whether a shell, and it sounds like really that is kind of what's going on here, is that could that be a result of a precursor ejecting a fraction of the envelope, or what are we? Do we have a sense of the physical origin of that?
Yeah. So the two kind of contenders that I think are most maybe promising for this. So there's some ideas that in the very late stages of nuclear burning, when the temperatures in the core get extremely high, you get these instabilities that are able to kind of propagate to the surface, and then you kind of shed. So for a 1 CBL progenitor, you're shedding a little carbon oxygen layer out. And that is what we observed. So in the spectra of the transient, we saw carbon and oxygen at absorption. So that's presumably the composition of this layer. So I guess that's the sort of wave-driven mass loss as one possibility. And then I've also read ideas that also because of sort of the late stages of nuclear burning, you might get a rapid spin-up of the progenitor, and that might cause equatorial mass loss. And so perhaps that's the way that this kind of material got there. So those are two possibilities that I'm aware of, at least.
Can I ask a sort of follow-up question? And Avi, if you have follow-up questions, or anyone, if you have follow-up questions, feel free to chime in. Say there's equatorial mass loss. Does that, in a sense, presumably that's the same equator that a jet would go out through the poles of?
Right.
So does the fact that we're seeing this strong interaction really kind of point towards the spherical story that you're raising, in the sense that, a jet might escape through the poles where there isn't much CSM in that? Does that make sense, or do I need to explain myself again? I know I wasn't very clear.
Oh, no, that's fine. Sorry. So are you asking if the material is just along the equator, you would not see the strong interaction?
Well, say there were then a jet in the pole.
Yeah.
You might have a relatively evacuated pole, but a dense torus. And the fact that you do see the interaction in some of these cases, if it ends up being an equatorial mass loss, sort of wave-driven in a rotating star, maybe that would point towards the geometry being not that of a sort of polar jet.
Oh, I see. Well, so I think maybe I wasn't clear. So I think that the emission that we saw was not anything to do with a jet. I think it was the spherical supernova explosion. I thought it was the supernova ejecta hitting the shell.
I see.
So no jet. Right. Despite this being a 1 CBL, and I looked very hard for a jet, I don't think we basically, I'm not involved with that at all in the model for this object.
Yeah, interesting.
I will say my personal opinion on 1 CBLs at this point is that not all of them have jets. So, yeah.
Could I just follow up on what Morgan was saying? So if there was a binary companion close in, could that imitate a shell for you?
That's a good question. I've not looked into that. I don't know why. I would have to, I don't know off the top of my head.
Because in principle, the collision of the ejecta with the companion could lead to some kind of a shock.
Yeah. I don't know how one would tell the difference between those scenarios. I would have to think more about that.
Let's close with one last question, I think taking us back to almost some of your final slides, thinking about you know, what the constellation of facilities that we have available and how do we make progresses. From Selma Demink, do we expect LSST to contribute to finding more of these fast rise events, or are they too fast to find there with the Rubin Observatory cadence? And do you need to, you know, use that only for the progenitors or something?
Yeah, I mean, yeah, so the nominal LSST cadence, the sort of what it's spending most of its time doing, is not well suited to this kind of thing at all. I think LSST is trying to make plans for sort of smaller scale, high cadence surveys, and I don't think a final decision has been made about that. So I think the sort of ideal combination is you have a shallow survey kind of running alongside LSST, where with your shallow, high cadence survey, you pick up all these fast luminous things in the relatively nearby universe out to redshift 0.1 or 0.2. And then with LSST, you do the pre-explosion studies and maybe even post-explosion studies. So
thanks, Anna. If I can specify, yeah. I guess I know it's pretty bad, so it was kind of a setup question. But the interest of LSST is also for rare events, especially if you can find them further away. And this seems to be something exotic. And the further away we can see things, we get a very interesting constraints. And if there's some sort of evolution with time and possible vitalistic, etc. So I'm hoping in the direction. Do you think that is hopeless with LSST because we can only do it nearby? Or?
So I think that what would help, so something I've been thinking about and trying to get involved with at Berkeley and LBL is whether you could avoid some of these cadence requirements by knowing the luminosity of the transient a priori. So what's distinct about these events is not just that they're fast, but also that they're quite more luminous than ordinary supernovae. And so if one had a very extensive galaxy catalog of galaxy redshifts, you could select these perhaps without requiring the same high cadence. And so then with something like LSST, maybe you could increase your yield of these types of events.
I think a pain to work out the selection effects later and understand what population they came from.
Yeah. And then there's the issue of you'd have to confirm what they are. And if they're too high redshift, maybe the radio emission wouldn't even be, or sorry, I'm thinking about 18 Cow when I was saying that. But if you wanted to get spectra to confirm this is a 1 CBL, then at higher redshift that could be extremely difficult. So there is the issue of spectroscopic confirmation as well.
And if I may, on the progenitors, there may be, depending on what the rate of these events are, there's also an interesting progenitor where you have a late time merger of two stars that either already stripped or have lost most of their events in previous interactions that could lead to ejection at late time and a merger not too long after. The question is if the material is still around. We haven't worked this out in great detail or discussed it in context of this, but with Emmanuel Zapatas, we make estimates for such events and where they would occur.
Oh yeah.
So that's maybe one. I'll send you a reference. It's not specifically addressed to this system, but depending on the rate, it could be relevant or not.
Okay, yeah, it would be great to talk about that more later. Thank you.
Anna, thank you so much for a really wonderful talk. Those of you who posted questions in the chat window, I recopied them into the Slack. And so, and for example, the link that you were just mentioning, Selma, that's a great place for it. So we can continue to congregate there. And we're so grateful for your taking the time to meet with us despite the challenges of life these days. So thank you.
Thanks so much for giving me the chance to be here.
Thanks, Anna.
Okay, talk to you all on Slack, I guess.
Yeah. Thank you for a nice talk. It is time to move on. Our next speaker today is Akon Fomik, who got his integrated master's degree in physics from University of Mumbai, and then moved to Carnegie Mellon for a PhD. And so this more physical-oriented background really shows in some of the work he has done at CMU, where he applied group theory to plasma dynamics and morphology. But the topic of his PhD thesis was actually measuring clustering in the early universe using the blue tides simulations. He has since moved to University of Florida, where he is working with a familiar person to the ITC, Laura Blecka, and actually studying the populations of supermassive black holes in Illustris, which we'll hear about today. So take it away, Aklant.
All right, thanks, Anna, for the kind introduction. And thank you so much for letting me be here and talk about my work. So I'll be presenting some results from a very recent work of ours, which I did with Laura Blecker and her student, July Thomas, on the impact of environment on supermassive black hole fueling, or AGN activity in the illustrious TNG. Can you guys see the slides okay? Awesome. All right. So the fundamental question that we try to ask with these kinds of works is essentially, what are the key physics that drives AGN activity in galaxies? So for a physical process to drive AGN activity, there are two key requirements that need to be satisfied. The first is that we need a steady supply of cold gas, and then we need some mechanism for the gas to lose its angular momentum. There are two broad categories of processes that can satisfy these requirements. On one hand, one can have secular processes that can occur within the galaxies, and these include stellar winds, gas accretion, or hydrodynamic instabilities such as the bar instability. On the other hand, one can also have galaxies being subjected to external disturbances such as major mergers or interactions, and that can also potentially trigger AGN activity. And this is going to be the focus of this particular work and talk. So galaxy mergers or interacting systems are also very interesting because they are precursors to what would eventually go on to form gravitationally bound black hole binaries, which are going to be sources of gravitational wave detections in upcoming facilities such as LISA. And this offers a very exciting prospect in the light of the upcoming era of multi-messenger astronomy. So in terms of the role of galaxy mergers or interactions in driving AGN activity, so there are two key fundamental questions that need to be answered. The first is whether a merger-AGN connection exists in our universe. And second is, if it does exist, what is its relative importance compared to secular processes in driving AGN activity, and whether there's a dependence on luminosity or redshift of the AGNs in terms of the answers to these questions. So observationally, we find actually that a vast majority of AGN hosts do not show any signatures of recent mergers in their morphology. And here are some examples of AGN hosts which have been analyzed in some recent works. And even visually, you can see that these hosts do not have any kind of external disturbances that would be typically characteristic of mergers or interactions. On the other hand, galaxies that are indeed found to be merging or interacting, they do tend to have a higher fraction of AGN hosts. And here's a recent work which shows some images of such interacting systems. And here's the result from Ellison et al. 2013, where they essentially looked at the AGN excess defined as the AGN fraction of merging or interacting systems divided by the AGN fraction of a matched catalog of isolated galaxies or non-merging galaxies as a function of the projected separation between the interacting galaxies. And what they found was that at decreased projected separations, there's increased AGN excess, which could be a potential signature of merger-AGN connection. So in terms of like what are the potential reasons for what are these conflicting results that can partially explain this conflicting results on the merger-AGN connection and its importance in driving AGN activity. So first, there could be like selection effects. For example, different observation groups use different selection criteria to select AGNs. You could select AGNs in the X-ray band or the mid-infrared or the optical band. And the point is that these different selection criteria could probe galaxy mergers at different stages, which could lead to different results. And then the second is that mergers can potentially trigger quasar obscuration. And this has been established in various works on simulations as well as observations. And here's an example result from Blecker et al. 2018, where they looked at idealized simulations of galaxy mergers, which is shown here. And they essentially investigated the AGN luminosity and the hydrogen column density as a function of time. And around the time of merger, which is here, we find that the AGN luminosity peaks, but so does the hydrogen column density, which could potentially obscure the quasar. So this essentially tells us that there's a significant portion of quasars that could be triggered by galaxy mergers or interactions, but because of obscuration, they may not be available for detections in various bands. So overall, what we see is that there's about the merger-AGN connection, there's very mixed results on the observational side. So there's a body of works that serve as evidence against merger-AGN connection and its importance. And there's another body of works that serve as evidence for merger-AGN connection. But this essentially tells us that this is a very active field and it's a matter of considerable debate. And there's a lot of progress going on, but a lot of further work needs to be done before we attain a much more complete picture. So the question that we ask in this work is whether we see enhanced activity, AGN activity associated with galaxy mergers in cosmological hydrodynamic simulations. And we essentially looked at the illustrious TNG simulation, which a lot of people in this session are very closely involved with. And these are essentially a suite of simulations which run all the way till redshift 0 using the ARIPO hydrodynamic code. The ARIPO code has a wide array of physics, which include gravity, gas magnetohydrodynamics, star formation, black hole growth, and stellar and AGN feedback. Here, I'm going to be focusing on results from the TNG 100 box, which has a box size of about 100 megaparsecs and about 10 billion particles. And with such a combination of volume and resolution, we are able to resolve not just the overall large-scale structure, which is shown in terms of the dark matter density field over here, but also individual galaxies and black holes, which are represented by these insert panels. So in this work, we essentially exploit the fact that galaxy mergers would organically lead to formation of closed systems of black holes within various separation distances. And we essentially identify these black hole systems in the simulation and analyze their AGN activity. So here's a schematic which kind of demonstrates our approach. So this black dots over here represent the spatial distribution of a very small example set of black holes that would be formed in the illustrious TNG box. And what we do here is basically link together these black holes using a maximum distance criterion, so which is denoted by Dmax and the horizontal line over here. So if you were to, for example, apply this criterion to this particular set of black holes, it would lead to the identification of this black hole triple system over here at the center, such that each member of the system is linked to at least one other member of the system within the separation distance Dmax. So we apply this criterion and identify black holes in the TNG 100 box at various redshift snapshots. And we probe different separation scales, which are meant to be proxies for different stages of galaxy or halo mergers. So here we consider separation scales of 1 megaparsecs, 0.1 megaparsecs, and 0.01 megaparsecs. So for example, 1 megaparsec separation scales would correspond to typical distances between black holes living in two different halos that have just merged or are close to merging. So this represents a very, very early stages of galaxy mergers where the galaxies are still, their host halos are merged, but they're still too far apart to be considered as interacting. And here's an example of such a system in this image over here, where the background panel shows a gas density field where going from dark red to bright yellow implies increasing gas density field. And these green circles correspond to the positions of black holes, which here we see it forms a triple system within 1 megaparsec scales, but their host galaxies are still too far apart to be interacting. And then we also consider scales of 0.1 megaparsecs, which corresponds to typical distances between black holes hosted by interacting galaxies. So here's another example of a triple system where one of the black holes is hosted by a very massive central galaxy, and the other two are hosted by satellite galaxies. And you can see that the central galaxy is kind of tidally stripping the two satellite galaxies. And lastly, we also consider separations of 0.01 megaparsecs, which corresponds to typical distances between black holes hosted by merging galaxies. So galaxies have already merged, but the black holes are in the process of merging. So, but with this separation scale, I have to mention the caveat that this sample is highly incomplete because a vast majority of these systems, because of the finite resolution of the simulation and the black hole repositioning scheme applied within the simulation, they would promptly merge. So it's a very incomplete sample, but nevertheless, it is worthwhile to look at the AGN activity of these systems as well. And the other thing I want to note is these separation scales are much, much larger than what would be associated with gravitationally bound black hole binaries. So again, due to the resolution limits of the simulation, we are unable to probe scales much smaller than this directly from the simulation snapshots. But on that note, I must also mention that there are various members of the group who work on post-processing models, which take these systems and trace the late time evolution of these systems using these semi-analytic post-processing models all the way down to scales of subparsecs. Okay, so now let's look at the overall statistics of these black hole systems in the TNG 100 box. So here we are essentially showing what we call the black hole multiplicity functions. So in the y-axis, we have the number of black hole systems plotted as a function of the so-called black hole multiplicity, where the multiplicity of 1 represents a black hole single, 2 is a pair, 3 is a triple, and so on and so forth. When we go from left to right panels, it represents decreasing separation scales from 1 megaparsecs to 0.01 megaparsecs. And as you can see that as we decrease the separation scale, the total abundance of these rich black hole systems of pairs, triples, and quadruples, they decrease as what you would expect. And this leads to an overall steepening of these multiplicity functioning profiles with decreased separation scales. Now, if we read off the numbers at, for example, redshift 0, shown by this blue curve over here, at 1 megaparsec separations, you have about 3,000 pairs, 700 triples, and 100 quadruples. At 0.1 megaparsec separations, you have 600 pairs, 100 triples, and 20 quadruples. And at 0.01 megaparsec separation scales, we have 60 pairs. But again, remember that the sample is highly incomplete because of the prompt mergers happening due to black hole repositioning and finite resolution. Okay, so now let's look at the AGN activity of these black hole systems. Here we quantify the AGN activity in various ways. So first we look at the so-called AGN fractions, which is the fraction of black hole systems at various multiplicities, which have at least one active AGN above a certain critical Eddington ratio. So here I'm presenting to you Eddington ratios greater than 0.7, and again plotted as a function of multiplicity. So if you look at the dashed lines accompanied by the green dots, these essentially represent the AGN fractions of randomly selected sets of black holes. And that fact that that increases with black hole multiplicity is a simple reflection of combinatorics, where we are saying that if we select larger and larger subsets of black holes, then the probability of at least one black hole, even if you randomly select it, at least one black hole will have a higher, will increase. It'll have increased probability to have at least one member at Eddington ratios greater than 0.7. However, if we compare these rather trivial increase to that of the solid lines, which corresponds to AGN fractions of true black hole systems, we see that particularly at scales of 0.1 and 0.01 megaparsecs, which, if you look at the ratio plots, which shows the AGN fractions of true black hole systems divided by that of the randomly selected sets, there's enhanced AGN fractions for these black hole systems by up to factors of 3 to 6 at these separation scales. However, if we look at the same effects at 1 megaparsec separations, we do not see any enhancements. Conversely, we can also start with a sample of AGNs at high enough Eddington ratios and ask the question of what fraction of this sample of AGNs are associated with companions within various separation scales. So here we plot this quantity in the y-axis, which shows the fraction of AGNs with at least one companion, plotted as a function of the Eddington ratio threshold. And again, we are comparing the solid and the dashed lines, where the solid lines are true black hole systems and the dashed lines are randomly selected sets of black holes in the ratio plot over here. And again, we see that at scales of 0.1 and 0.01 megaparsecs exclusively, if we look at the highest Eddington ratios, these AGNs have enhanced likelihood of being associated with companions by up to factors of 4, compared to what you would expect from a simple random selection. However, if we look at the overall fractions, we must also note that while there is enhancement, but the overall fraction of AGNs that have companions at 0.1 megaparsecs is still 40%, which means about 60% of them are still not associated with companions. So their AGN activity is likely driven by secular processes. The same enhancements, if we try to look for them at 1 megaparsec separations, we do not see any enhancements, as you can see here, similar to what we found for the AGN fractions. From an observational perspective, it is also interesting to infer as to what fraction of observable AGNs have companions. So I'll start with showing some results for local AGNs. So these are results at redshift 0 snapshot. So here we are essentially plotting the fraction of AGNs with at least one companion again, but as a function of the flux threshold of the in the 14 to 195 kilo electron volt band. So essentially the ultra hard X-ray AGN band. The blue and the orange lines correspond to the 0.1 megaparsec and 0.01 megaparsec separations respectively, where we did see AGN enhancements. And if we infer the results at the Swift BAT flux limit, we find that about 20% of Swift BAT AGNs have companions within 0.1 megaparsecs, and about 2% of the Swift BAT AGNs have companions within 0.01 megaparsecs. If we move to higher redshifts, there's the Swift BAT AGN. So the AGNs are too faint to be detected within the Swift BAT survey. But in the hard X-ray band, there are some surveys which can potentially detect AGNs. So here are results of the same quantity, but plotted now as a function of the flux threshold of the 2 to 10 kiloelectron volt, which is for the hard X-ray band. And these vertical lines show the various flux limits of the various surveys in the hard X-ray band. So the extended Chandra X deep field, the Chandra deep field, and the Stripe 82 ACX. And if we infer the results numbers for the Stripe 82 ACX survey, which is the widest of all these surveys, we have about 30% of these Stripe 82 AGNs that have companions within 0.1 megaparsecs, and less than 1% of these AGNs have companions within 0.01 megaparsecs. Okay, so lastly, I would also like to quantify the impact of these merger-driven enhancements on the overall Eddington ratios. So here I'm showing the median Eddington ratios as a function of the redshift, where for black hole singles shown by the black lines, black hole binaries shown by the maroon lines, and the black hole triples shown by the purple lines. And again, if we focus on the comparison in the solid and dashed lines, which is true black hole systems and random sets of black holes, respectively, we see that the median Eddington ratios for the true black hole systems are enhanced by up to factors of 2 to 3 at scales of 0.1 and 0.01 megaparsecs, but there's no such enhancements at scales of 1 megaparsecs. And then additionally, we also find that these enhancements are more prevalent at higher redshifts compared to lower redshifts. And this is naturally occurring because there's higher availability of gas to fuel these mergers at higher redshifts. So overall, to summarize my talk, we investigated the AGN activity of black hole systems in TNG 100, and we found enhanced AGN activity, which manifests in the form of enhanced AGN fractions by up to factors of 3 to 6 for these very high Eddington ratio AGNs at scales of 0.1 and 0.01 megaparsecs. Conversely, if we also start with a sample of AGNs and look at what fraction of them have companions within 0.1 and 0.01 megaparsecs, we see enhancements in that likelihood by up to factors of 4. And then given the fact that no such enhancements are found at scales of 1 megaparsec, this hints that these enhancements are likely driven by mergers, galaxy mergers or interactions. However, we also find that despite these enhancements, only about 40% of AGNs actually have companions at 0.1 megaparsecs, and even less so for 0.01 megaparsecs. And this tells us that a vast majority of these AGNs are still driven, but likely they don't have companions, and they are likely driven by secular processes. And then we also find that these overall enhancements in Eddington ratios in these black hole systems are at best up to factors of 2 to 3. And this finally tells us that while merger-AGN connection definitely exists in the illustrious TNG simulations, they play a relatively minor role in driving overall AGN activity and black hole growth as compared to secular processes. And with that, I conclude my talk. Thank you again for the invitation. In addition to these works, I also work on, I'm currently working on black hole seeds, implementing black hole seed models, realistic black hole seed models in cosmological hydrodynamic simulations. So I'm currently running Zoom simulations to investigate that. So if anyone is interested and would like to discuss more on that topic in addition to this particular one, feel free to ask any questions. Thank you so much.
Thank you. Thank you for a really wonderful talk. So I want to open with 2 questions from Martin Elvis, who asks, have you considered or tried the new star 8024 KeV band, because there would be less obscuration there?
Okay, so I haven't tried that, but one reason why I selected
8 to 24, sorry.
8 to 24. No, I did particularly look at that yet. I wasn't aware of that as well. But one reason why we looked at the ultra hard X-ray band was that that was least prone to obscuration, and that's also where we looked at compared our results with observations from Cost et al. 2012, and they were numbers were consistent. But of course, for the hard X-ray band, it's significantly much more prone to obscuration, so we could not. But yeah, that's a very interesting point. We should look at that, the new band that you considered.
Interesting. And second, in number metallicity, like in that relationship, there seemed to be no evolution for redshift less than 1.5. And this seems surprising as there are a lot of AGN, there's a lot of AGN evolution from redshift 0 to 1.5. And maybe mergers aren't responsible.
So you mean the overall abundance of black hole systems here?
And Martin, if you'd like to unmute yourself and chime in. Yes.
Okay, so
the colored curves, blue, red, and green are all on top of each other. So there's no change.
yes, I mean, they decrease, but not to such an extent between redshift 0 to 1.5. But if you look at the overall AGN activity, they are. So if you were to make the same plot for the abundance of AGNs, then at various flux limits, right, then we would see an evolution. So the AGN activity significantly decreases between.
So that suggests that the connection with the multiplicity is not that strong. Is that right?
That simply is a consequence of the overall decrease in the AGN activity, but mergers can still be triggered, but because of the availability of less gas, but to a lesser extent compared to redshifts, higher redshifts where you have more gas.
Interesting. From Avilob, what is the fraction of pairs that produce a gravitational wave signal that's detectable by LISA, which show AGN activity in tertiary or higher order multiple companion? So pairs that produce a gravitational wave signal which have AGN activity in a third.
Yeah, that is an interesting question. I haven't looked at that yet. So there are post-processing models that a student of Laura Bleca, Mohammed Saeed, is working on, which does predict, make predictions for gravitational wave detections for these kinds of sources. And yeah, I mean, I think that's an interesting avenue where we can actually collaborate together and figure out, I mean, I can look at the AGN activity and you can look at the gravitational wave, but at this point I haven't looked at that because we have to apply these models to smaller scale and trace their evolution to smaller scales.
Fabulous. So I was wondering along those lines, obviously there is a resolution limit to any simulation, but can we say something about, could one apply essentially a subgrid model of the in spiral and perhaps merger by basically asking if there is a single black hole which was multiple but merged at time X in the past in the simulation? So in a sense, like, can we get some information about what may be a subgrid pair by asking about singles that are previous mergers?
So you mean that we start with a sample of in the simulation, because of prompt merger they're appearing as single black holes, but
yes,
but actually they are, like, if you were to have an infinite resolution simulation, for instance, they would be merging black. And I mean, it's somewhere along those lines that these post-processing models that Saeed et al. 2020 is trying to apply. So they're basically taking these
exactly
and trying to trace. So one thing that they do is incorporate delay times in their mergers. So one of that important aspect of the model. And yeah, it's definitely possible to do that. And yeah, I mean, we can move forward that discussion with Saeed and look at that avenue for sure.
Great. And we have time for one last question. Hiran Chow asks, what kind of black hole feeding model are you considering to implement in the cosmological simulation? And then assuming a repo, will you be abandoning the Bondi-Hoyle model, or what's your plan?
So currently we are running a whole bunch of tests just to determine that. So we initially started off with a very simple model where we replaced the FOF based seeding, where you just seed in FOF groups at above a certain mass. We have replaced that by seeding at FOFs where the densest gas cell has just become star forming, but the metallicity of that specific cell is less than a specific value. So we have considered various 10 to the power -4, 10 to the power -5, and we have run some initial tests. And And then we are also considering various other models, for example, like the star-forming gas mass of that specific halo is greater than a certain factor times the seed mass, for instance, or the metallicity of the star-forming gas is less than a certain value. So we are trying to do various possible tests to investigate that and see whether the key problem here is that we have to achieve, in some sense, a resolution convergence because what we are really trying to do is because we cannot resolve these seeds at these limited resolution simulations, we are trying to we are trying to seed these simulations with the resolution of the simulation, which is limited. And we are trying to infer the evolution by running higher resolution zoom simulations as to what would happen if the seed, which would have otherwise been seeded a lot earlier, would have evolved to a much larger mass, and then we can seed that larger black hole mass into a lower resolution simulation. And that's a very tricky problem because there's so many different environmental factors that affect these and the evolution of the black hole seeds, like halo mass, metallicities, star formation histories, and all of that. So right now we are undergoing a lot of tests, and we haven't absolutely narrowed down on which fiducial model we want to use, but we are doing that.
It's really interesting. Well, I think we are at our time. So let me thank both you, Aklant, and Anna for really wonderful talks today. And we all want to express our gratitude for your joining us and convening in this virtual space. So thank you all.
And thank you all for tuning in. It's really nice to at least see the handles of more than 60 people from the CFA and ITC.
Exactly. Wonderful. Well, we'll see you all soon. Bye-bye.
Yeah.
Thank you.
Next week. Bye.